Okay, let's get going here. Uh, Welcome, everybody. We are at the beginning of Project 4, which is sort of the capstone project that you're doing in teams of 4 and such. We handed out the code on Tuesday but didn't make repositories. And part of the reason for that was that we were still tuning up the bot and tuning up the documentation and trying to make it more accessible and hopefully more correct as well. And so among the things that we've decided to do is we've changed the starting position from what was in the notes, but the handout that you haven't lost anything by looking at it. You've gained something, frankly, but some of the details are different. So there will be a replacement doc for that, and in your repositories you'll have the real code, which is 99% the same. But there are some things that I think we've improved and that'll give you a better experience as you start working on your code. Today we're going to do a code walk, and it's my great pleasure to introduce Tim Kaler. Tim is a postdoc and lecturer, and you may not be aware, but he has actually been behind the scenes in this class since September. And he's one of the people who has, he's the person who built much of the cloud infrastructure that you're working on, and has built up the infrastructure for this chess game. And so he's going to do the code walk with you folks, and I'll chime in if Tim feels that that he needs comic relief. So Tim, take it away.
Yeah, thank you very much, Charles. Yeah, I can't take too much credit for this year's infrastructure. So I've done a lot of work on the infrastructure in this project in the past, but especially this year, the TAs Ravi and Nick and Chi-Chi and basically the whole core staff has put a lot of work into the infrastructure and this project in particular.
Alex as well, yep.
Alex, yes, I'm sorry, Alex as well. Today I'm just going to kind of give you an overview of what the final project for the class is and give you some background information on game playing programs. So the project 4 this year is going to have you design a game playing program for a game called Leiserchess. So Leiserchess is like chess played on an 8x8 board. And there are 2 types of pieces. There are kings and pawns. And if you look over here to the right, I'll show you kind of the basics of how the game mechanics work. So there are 2 players. One is Tangerine and one is Lavender. And Tangerine moves first in the game. And during a move, Tangerine is allowed to move any one of its pieces. So I can move the king here, right? Or I can move one of my pawns to any one of the 8 adjacent squares, like so. Additionally, I can rotate a piece if I wish. So I can, instead of moving a piece, I can do a rotation to any one of 4 orientations for either a pawn or a king. And after my move, so if I decide to move this pawn, for example, I can fire my laser. And the laser will bounce off of the long side of the pawn, which you can think of as having a mirror on it. And the ultimate goal is to try to shoot your laser at the enemy king by finding a path by bouncing off of the mirrors on the pawns from your king to the enemy king. So I'll just play a quick game between 2 computer players just so we can see a few moves. Okay. Right. So here's just an overview of the rules. As I said, during each turn, you will move a piece, and then your king will fire its laser, and your king is required to fire its laser at the end of each turn. And the win condition is when the other king gets zapped by the laser. There is a new mechanic this year in Leiserchess in 2020. Each year we try and find new and interesting ways to change up the game. And this year, the mechanic that we've chosen is this idea that the pawns conduct the laser to adjacent pawns that they touch when they are hit. So if you take a look at this example on the left, I'm going to stop this for now. This example on the left, the lavender pawn has made an interesting play where it has decided to turn its king so that it will zap the back of its own pawn. And by doing so, it has destroyed two tangerine pawns because this lavender pawn is touching each one of these tangerine pawns at least one corner. So the result of this move is lavender will lose one pawn, but tangerine will lose two pawns. And you notice that this lavender pawn right here is not destroyed because it doesn't touch any of these destroyed pawns at any point. Okay. Does this make sense? So if anyone has any questions during any point, just post it in the lecture Slack channel and it will pop up for me. Okay. So there's some interesting tactics in Leiserchess. The win condition, as I said, is you want to find a path where your laser can hit the enemy king. But the challenge is that often when you try to make an aggressive move in Leiserchess, you actually open up your own king to an attack. So here is an example of a board configuration. And let's say that you, as tangerine, want to try and zap the lavender pawn on f5, which is right here. Okay. So what move could tangerine make to try and zap the lavender pawn on f5? So we can kind of trace out the path of the laser to kind of get an idea of what we might do. E2. There we go. Yeah, C2 to B1. Very good. Yes. So we move, if we move the pawn C2 to B1, then the laser path will take this route and it will destroy the lavender pawn on F5. But here's the downside of making that move. If we do that, lavender can counter by moving its pawn on D6 to C7, and it will zap the tangerine king and win the game. So you have to be very careful because whenever you make kind of an aggressive move that sets up a king to laser path to an enemy piece, you're potentially exposing yourself to being zapped along a similar path by the enemy king. Okay. So the way that we play these games is similar to chess. We essentially will give each player we'll time the players the same way players are timed when you play chess. So we use Fisher time control, where each player is given a fixed time budget and an increment. So for example, if we used Fisher time control with a budget of 60 seconds and a time increment of 0.5 seconds, then you would have 60 seconds of time to use however you wish. And each time you make a move, half a second will be added to your total time budget. And when you are creating your computer programs to play the game, those computer programs will be constrained to make moves within the time constraints of this Fisher time control. Okay, and a draw in the game occurs if there's been 100 moves by each side without a pawn being zapped, or if the same position repeats itself 3 times with the same side to move, or if 2 players agree to a draw. But that only happens if you have 2 humans playing against each other, because computers are heartless. Okay, and the web GUI, which we will provide you in your repository, will allow you to play games either between a human and a computer, between 2 computer bots, or between 2 humans, if you like. And we recommend that you watch a few games of the bot playing itself to gain some intuition for the game. Okay. A few things, a few little details that may be useful for you to know when you're trying to manipulate the bot using the web GUI is the fen notation that is used to describe positions. So the fen notation is displayed in the web GUI for the current position under right here on the right in state. And if you have a particular position that you want to investigate using the web GUI, you can enter in the state that you wish to explore into this field right here, and it will set the board to that state. So for example, if I wanted to set the board back to the opening position, I can copy this fen string, paste it in, and set the board, and I'm back at the opening position. And the basic notation here for the fen notation is that the rows of the board are separated by forward slashes, and then the pieces are enumerated in each row. So for example, if we look at the last row of the board, there's 3 tangerine pieces, a king and 2 pawns. And so we look at the last row of the fen string, and we see that it's telling us that the first location has a king facing east. It then has 3 empty squares. Then it has a pawn facing southwest, 1 empty square, and then a pawn facing northwest, followed by 1 empty square. And the total number of squares, if you add them all up, is always going to be 8. Okay. So you'll get more comfortable with this notation as you play around with it more. But it's very useful, especially if you have some interesting positions that you come up with that you want to investigate in more depth. It's useful to know this notation. Okay. So let's jump right into how the project code is organized. Okay, so the project 4 repo has a number of directories here. So the top level ones are tester, tests, player, and web GUI. The tester directory contains a bunch of tools that are going to help you run games and evaluate your bot's gameplay and performance. So this includes a Java auto tester, which will let you run local games between your bots. You can use this to run hundreds and hundreds of games to test your gameplay and performance. And then we include a bunch of tools that will allow you to take the records of the games that you run and understand various statistics from those game results, such as the computed ELO ranking of different versions of your bot. And also things like the average depth that your bot searches and other statistics. And we'll look at these tools in a moment with some examples. Then there's the player directory, which has the actual code for your Leiserchess bot. And this is where you're going to be spending the bulk of your time. This actually contains the code that you're going to want to optimize. And then there's the web GUI, which I just showed you, which will let you run local games and such. Okay, so let's take a look we're going to first take a look at how we're going to test your bot's gameplay and performance. So if I go into the player code, I can build my bot just by running make, and it will create a Leiserchess bot. I can run Leiserchess, and I can say display to display the current position. I can type UCI to get various options that are available for me to set in the bot. And I'm able to tell it to do a search, such as a depth 5 search. And I'm able to tell it to make a move, such as move, rotate the piece on E0 to the right. The interface that I've just shown you is called the UCI interface. And this is the universal chess interface, and it's a communication protocol that allows you to programmatically communicate with your bot. And this interface is used by the auto testing system in order to automatically run games between two bots. And it's also useful for manual testing if you want to manually make a few moves to evaluate that your bot is playing correctly. Okay. So using the UCI interface and the auto tester, we can test changes between different versions of the bot using either time trials or fixed depth testing. And the configuration file for the Java auto tester looks like this. So you specify the number of CPUs that you want to use to run the test. So in this case, we're going to run using 12 CPUs, which means we're going to run 12 games in parallel. You can specify an opening book. If you don't specify an opening book, that's okay. It just means all of your tests are going to be run from the game's default starting position. And then you specify the number of games you actually want to run. So this file is running 500 games in total. And then you provide a list of the players that you want to play against as part of this test. So in this example, we are playing, we're testing two different binaries. We're testing the Leiserchess binary, and we're testing the Leiserchess with some change binary. And we are using Fisher time control for both bots with a pool of 20 seconds and an increment of 0.5 seconds. Okay. So as a quick example, let's take a look at, let's actually run one of these auto tests. So this auto test that I have here on the right is going to run 8 games, and it's going to compare two different players. The first player is player depth 3, and the second player is player depth 5. And this is going to be a fixed depth test. So instead of using Fisher time control, I'm going to tell each bot to run a search to a fixed depth in the search tree. And one is going to search to depth 3, and the other is going to search to depth 5. Okay. I run this test by invoking the Java auto tester inside the tester directory. So I'll just run that and see what happens. And it tells me that it gives me usage instructions. So I have to provide it a path to a referee bot. And the referee bot is going to make sure that both players abide by the rules of the game. And then after I pass it the referee, I'm going to pass it the auto test file, depth5.txt. And I'm going to go ahead and run that. And it's going to run 8 games for me. So this will just take a moment.
Maybe we take some questions while we're waiting for this to be done. So if people have any questions, you can unmute yourself to ask questions or ask in the Slack channel.
It's done now, but in general, feel free to use the Slack or unmute yourself if you like. I don't mind being interrupted. This is kind of a more the more interactive this walkthrough is, the better. But anyways, so this depth 5 test completed, and once it completes, it will generate a PGN file. So I look at the depth5.pgn file that was generated, and what it's going to have in that file is it's going to have a record of each game that was played. So the record for a single game is going to have some metadata telling me which player was player 1, which player was player 2. It's going to tell me the result of the game, which player won. And then it's going to have a list of the moves that were played in the game. And I can look at this manually if I like, but we also have tools that we provide you to automatically analyze these PGN files that are generated by the auto tester. One of these tools is called PGN rate, and that's going to be very useful to you to compute the ELO ranking of the different bots that you are testing. So if I go ahead and I run PGN rate on the PGN file, we see that the depth 5 player won 94% of all the games, and it has a higher ELO rating than the depth 3 player, which makes sense because the depth 5 player is searching with greater depth. Additionally, we have the PGN stats tool, which you can use. Which will show you things like the average amount of time that each player spent making its move. So because the player that searches to depth 5 has spent more time per move than the player that only searched to depth 3, which makes sense. It's also looked at more nodes, and it's and the average depth searched is exactly what we specified, 3 and 5. Okay. Let's look at one more example. Oh, go ahead.
What is log of R?
Log of R. That's a good question. I think that is related to we should probably get back to. So I think it is related to. It's related to the node counts. I think it is a comparison between.
I don't recall either, but there's documentation for this, and the PGN stats in particular is not our program. It's one that we have acquired, and so there may even be more web information about it. It's one that was originally developed for chess programs. And I don't recall what that is either.
Yeah, I'm pretty sure it's a derived statistic, though, from the other data that's provided.
And why we would end up with 2 columns that say log R. It's weird.
Right, yeah. Right, well, I think it's like a log of, all right, well, I shouldn't guess. I have a guess, but I'm not gonna, it might be, it's just a guess. So. Let's look at a different test. So here's another auto test that we might think to run. This is actually a test that we usually run when we are kind of verifying that the game is a good game for a performance engineering class. So in this auto test file, I'm going to run 100 games using 8 CPUs, and I'm going to play 2 players against each other. Both players are going to use the same binary, but one player is going to get twice as much time as the other player. So there's player little time, which only gets 5 seconds of time. And there's player more time, which gets twice as much. It gets 10 seconds of time to make its moves. And I'm not actually going to run this auto test live because it takes about 5 or 10 minutes. But I've already ran it and generated the the PGN file for it. And I want to just show you some of the statistics that you can generate, that you can from this test. So I'll first look at PGN stats. Okay. If we look at the time column, we see that the player more time used roughly about twice as much time on average per move than the player that used less time. And if we look at the average depth searched, we see that the average depth searched for the player with less time was about 4.05. And the average depth searched for the player that had more time was 4.6. So the average depth searched is a little bit higher for the player with more time. Now, how does that translate into actual game playing performance? Well, to understand that, we should use PGN rate to compute the ELO rating of the two bots. So let's go ahead and do that. And we see that the player that had twice as much time has a higher ELO rating and won 72% of all the games, which is more or less what you would expect. And so kind of one way to understand this result is that if you are able to make your bot twice as fast, then you're going to be able to increase the depth that your bot searches, and that's going to translate into your bot winning more games. So
I'm not sure you explained what ELO was.
Right. Well, ELO. So ELO is a rating system that's used in chess and other games. It is kind of a probabilistic measure of the probability of two players with two different ELO ratings winning. So is there a slide on that? Yeah. So for an exact mathematical description of ELO ratings, I'd recommend looking on Wikipedia. It's not that complicated. The essential thing to understand is that it's a way to measure the relative skill between different players. ELO ratings are always relative to a pool of opponents. Really what matters is not the absolute number that you see as your ELO rating. What really matters is the relative ELO ratings that you achieve within a pool of players. These ELO ratings that are generated using this PGN rate tool that I just showed you are going to be used to evaluate your bot's performance. And we're going to, in particular, compare your bot's ELO rating to the ELO rating achieved by a variety of reference implementations that will be created by the staff. Okay. So I want to just show you a few more fun things that you'll be able to, a few more fun tools that you'll be able to use when evaluating your bot before we move on. So let me show you the scrimmage server. Let's pull it up. So in addition to being able to run games locally using the web GUI and being able to run auto tests using the local auto tester, we also each year set up this scrimmage server, which is a website that will allow you to play games using your team's bot against other students' bots in the class. And these matches are purely for fun. Your grade doesn't depend on these matches at all, but each year teams usually have some fun by having some friendly competitions with each other. So the way it works is
just to reemphasize, you're not competing in this against each other. Okay, you are not competing against each other. You are not competing against each other. Okay, your score is determined by how you do relative to reference spots that we build, and you are not competing with each other. Okay, so But we'll have a tournament where you can compete with each other, but it's only for fun. But your grade is completely determined by the performance relative to the reference bots.
Yeah, no, that's absolutely true. We go to great pains to ensure that your grade doesn't depend on other students' performance. So if you want to do a friendly challenge game against either a reference implementation or against another team, you just pick out the team that you want to challenge and you send a challenge. And then you can watch the game as it's being played live using the Scrimmage website. And it's actually kind of fun to play games and watch them using the Scrimmage website. A lot of students find that they catch a lot of bugs actually by watching. The local Java auto tester is great, but it doesn't actually allow you to watch the games as they're being played. So a lot of times if you do tests on the Scrimmage server, you're able to actually see what caused your bot to lose a game and make some improvements based on what you see there. Okay. And then there's one more tool, I promise, and then we're going to move on to other stuff. There's one more tool I want to show you, and this is also another cloud tool. In addition to being able to run exhibition matches on the Scrimmage server, you are also able to run auto tests using the cloud infrastructure. Okay, so there's going to be documentation for all this, so don't worry if you don't catch it, catch the exact syntax that I'm using. But basically, we have this tool called auto test run. You can specify time control. So the time control modes are given different names. So there's blitz, regular time control, and long time control. And each of these correspond to a particular Fisher time clock. And you specify the number of games, 10, for example, and then you provide a list of bots that you want to run against each other. So in this case, I'm going to run demo test 1 against demo test 2. Running that command will upload the bots, and it will give you a link to your auto test. And so this uses the Scrimmage website as well. These are more or less private, or intended to be private at least. These cloud auto tests are just for you to evaluate your own bot's performance using all the machines that we set up in the cloud. Usually we set up 100 or 150 machines to run games in the cloud for the class. And you can, just like the other games, you can watch these live if you like. And after the game's complete, the result of base elo will provide you the elo rating of the bots that you used in the test, and it will also provide you the output of PGN stats, so you can see all the information that you need. Okay, and we'll provide documentation there will be documentation for using all these tools that will be provided to you. Okay, so those are the ways that you can use your bot and test your bot's performance. You'll be using all of them. I know it seems like throwing a bunch of tools at you, but all of these tools are very useful, and you're going to become intimately familiar with all of them. All right. Now let's actually dig into the player code. Okay, so Abe asked a question. Is there a way to get a CSV file of all the moves played in a game when we run the game on the cloud service? I don't think we have a way to provide you a CSV, but I do believe there's a way to get the raw log output from all the games played. If you ask that question on Piazza, once we, in a day or so, we'll be able to give you more precise instructions on how to do that.
Yeah, also, one of the things in this is a very cooperative activity on part of everybody, and people who contribute tools and things like this can help your grade. Okay, so if you're, for your participation grade, if you are contributing, if you say, oh, okay, wouldn't it be nice to be able to extract the moves from this, and you write a Python script or something that that gives you the CSV moves, and you post that on Piazza, big points. Okay, things that especially are tools that help other people, short segments of code that you want to share with everybody, all those, putting them up on Piazza really help your participation.
Right. Right. So basically, I think at this point, I hope that everyone kind of understands kind of the basics of the game. And if you had a program that you implemented to play Leiserchess and you implemented the UCI interface, you can kind of understand how you can evaluate the performance of your bot in terms of its game playing performance. We provide a lot of tools for you to do that. Now I'm going to talk a little bit about the actual mechanics of how you program the game playing bot. Okay, so the code for the game playing bot is in the player directory. I can compile it using make. The board in the game is represented in the program as an 8x8 array that is centered within a larger 16x16 board. And the reason we do this is so that we can have sentinel values around the board. This is useful when we fire the laser because we're able to detect when the laser goes off the board by simply checking to see if we have hit a sentinel value. So for example, if the lavender pawn shot its laser, we would be able to fire the laser along the board. We would hit this mirror. And then when we check this square off the board, we would see that that square has a sentinel value. And we will know that our laser has gone off the board, and we can stop tracing the laser path. There are certainly other board representations that are more optimized that you probably will want to investigate, but this is the one that we give you to start with. A position, which is this structure, which is in movegen.h, and it has an array for the board. So the board is an array of size, array size. Array size is going to be 16 times 16 because it's a 16 by 16 board that has an 8x8 board kind of in the middle. We have a history field, which tells you what was the previous position that occurred before the current position. There's a key, which is a hash key that is a hash of the current position that we use for various lookup tables. There's apply. This tells you how many moves occurred before this position in the game. We have a field that tells you how many plies occurred in the game before this position since the last piece was zapped by the laser. This is important when considering the draw condition in the game. We provide the last move, the move that led to the current position. We have this list of victims, which tells you which pieces were destroyed by the last move that was made. This is used for checking some end game conditions, for determining quiescent search and some other things that we'll talk about in a bit. And then a list of king locations, which is mostly for convenience. Technically, you could find the king locations by scanning over the entire board. But for convenience, we just include the locations of the kings right inside the position structure. Okay. So let's think a little. Let's explain how moves are represented in the game. So there is this move t type that is used to represent a move. And a move t is actually an integer type. And we represent moves as basically a packed integer. So 2 bits in the move t type are used to represent the type of the move that is being moved. And then 2 bits are used for the orientation of the piece. And then 8 bits are used for the from square, the square that the piece originated from. There are 8 bits that are unused, and then the last 8 bits are used to denote the square that the piece moved to. Okay. So just as an example, if the move corresponds to the rotation of a piece, then the from square will be equal to the to square, and the orientation will change. Right. And if the piece actually moves, then the orientation will stay the same, but the from square and the to square will be different. Okay. And we provide some helper functions for you to get and set the properties of a move given one of these move t types.
What's the purpose of the unused space exactly? Like, why not just not have that byte?
I think it's mostly, yeah, I don't think there's a particularly good reason for why the unused space is in between the from square and the to square. I think the unused space could just as well be at the end or the beginning of the type. I'm not sure there's a good reason for that. And you might be able to reduce the size of a move type to, I'm not sure that's such a big optimization, but you can probably represent a move more concisely than what we've done in the reference implementation if you desire. Okay, so how do we, given a position, how do we generate all of the legal moves that a player can make from that position? Okay, well, the move generation code is going to be in movegen.c, and there is this function that will generate all the moves from a given position called generate all. So generate all is going to basically scan over the entire board. So it's going to scan over the width of the board for each file in each rank. And then for each square of the board that has a piece, it's going to find all the legal moves that that piece can make. So it's going to consider all of the moves that that piece might make. So a piece can move to any unoccupied adjacent position. And alternatively, a piece can stay in its current square and rotate. So all the rotations for each piece are a legal move. And then finally, you're allowed to make what is called the null move, in which no piece moves and no piece rotates. But you're only allowed to make the null move if you're going to zap a piece with your laser as a result of the null move. So if your king is about to hit a piece, and if you don't move any, if you decide to not move any pieces, your king is going to zap one of the pieces on the board. Then you can make the null move and basically skip the move phase and just fire your laser. Okay. So this is the logic for generating all of the moves from a given position. Okay. Now, generate all is not actually a bottleneck in the code that we give you. However, after you start to make optimizations to other parts of the code, eventually generate all will become a bottleneck, and you're going to want to make performance optimizations to it. It is very important, as you might imagine, that when you change generate all, that you do not introduce bugs. And so whenever you make a change to generate all, it is very good practice to verify that its behavior is the same as the reference implementation by running this function called perf_t. So perf_t it's actually a UCI command. So if I run Leiserchess, I can run perf_t, and it will basically find all of the legal moves after for a certain depth in the search tree. So after 4 moves, there are this many legal moves. And whenever I make a change to generate all, I want to run perf_t to verify that I have not actually changed the number of legal moves at a certain depth. So whenever you change generate all, it's a good idea to run perf_t to verify that you have not introduced any bugs. Okay. How do we evaluate the quality of a position? So we have a static evaluation function that is in eval.c. And the static evaluation function is used to determine which positions are better than others. And we have a variety of heuristics that we use to make this assessment. There's a number of heuristics in the evaluation function. There is the k-face heuristic, which provides a bonus for your king facing the enemy king. And then there is a k-seed heuristic, which is a penalty that is given whenever you are giving the enemy king a lot of room on the board. And these heuristics are implemented in eval.c, and you can take a look at them. There's also some heuristics related to pawns. There's a material bonus. So you get a fixed bonus for each pawn that's still alive. There's the p-touch heuristic, which gives you a penalty for each pawn that's touching another pawn. The reasoning behind this penalty for p-touch is that if you have a lot of your pawns touching other pawns, then that makes them vulnerable if one of the pawns in that connected component gets zapped by the laser. And then there's the p-prox heuristic, which provides a bonus based on kind of summing the harmonic distance from each pawn to each king, with the notion being that if you have pawns close to a king, that gives you kind of control over that neighborhood around the king. And then we have some heuristics related to the laser. In particular, we have the L coverage heuristic, which provides a bonus based on how much of the board near the enemy king is covered by the laser after making all possible moves from the current position. The L coverage heuristic is hugely expensive. If you actually profile the code, you'll find that 85% of all the time spent in the search is spent inside L coverage. So as you're thinking about your optimizations, it probably makes sense to think long and hard about how you can make the L coverage heuristic faster. Okay. So in the last kind of 40 minutes that I have left, I want to just give you some background information on game tree search and on chess playing programs in general. Kind of just a quick survey over some of the concepts that are used in the reference code that we give you. So I'm just going to quickly go through the basics of game tree search first. So the simplest type of game tree search that you can have is more or less minimax search. So you can have this tree where you have 2 types of nodes. You have maximizer nodes and minimizer nodes. And then you have these leaf nodes. And each leaf node corresponds to a position that you're going to run the static evaluation function on. So you have all these leaf nodes, and you're going to run the static evaluation function on each of these leaf nodes to give them each a score. And then the maximizer is going to choose the maximum score from all these leaf nodes. And we're going to consider the score of this node here to be the maximum of all of its children. And then each one of these purple nodes is going to be a minimizer, and it's going to pick the minimum score from all of its child positions. And then finally at the root is going to choose the maximum of each one of these scores that are achieved by the minimizer. Okay. So we create these game trees using MoveGen and the static evaluation function that we just looked at. So if we start at a particular position, we generate all the predecessor moves by using the generate all function in movegen.c. And when we're at a leaf node, we determine the score for that position using the static evaluation function that's in eval.c. Okay. Additionally, we make sure that the positions that we're running the static evaluation function on are stable. And so the basic reasoning behind the basic problem of doing a fixed depth search is that sometimes you will capture a piece, but in the very next move, after you capture a piece, the enemy may be able to take one of your pieces as well. And if you do not actually, if you only do a fixed depth search, then you will not see that, you'll incorrectly believe that you have a material advantage. When in fact, if you expanded the tree one depth further, you would find that your material advantage only lasted for one move and the enemy would just take the piece back. So quiescent search basically extends the search until you're at a position where no pieces are being captured. And we implement that in the reference code that we give you. In general, with game tree search, the deeper that you search, the better your bot will perform. So this is just a little a plot that shows the relationship between the ELO rating of bots with respect to the depth that those bots search. And as you can see, as the depth on the x-axis increases, the ELO rating of the bot increases in a pretty direct fashion. Similarly, if you look at the total number of nodes that are evaluated by different bots, bots that evaluate more nodes tend to have higher ELO than bots that evaluate fewer nodes. Okay. Now, of course, we don't actually we don't actually implement minimax search. We in fact implement something based on alpha beta search. So alpha beta search is basically a search tree pruning strategy that eliminates subtrees from the minimax search tree so that you can evaluate fewer nodes when you're doing a fixed depth search. Pure alpha beta is guaranteed to give you the same result as a minimax search, but it does so while evaluating fewer positions. The basic idea behind minimax search is that you can sometimes the maximizer or the minimizer will discover a move that is so good that the other player would never allow that position to occur. And so as soon as such a bound on the score is found, a player can skip searching the remaining positions because it knows that the other player will never allow that situation to occur. Right, so if we go through this example real quick, the maximizer finds that its maximum score in this left subtree that it can achieve is 6. The minimizer knows that it can achieve a score of at least 6 if it takes this path in the search tree. But it doesn't know if these positions are better or not. Maybe these positions are better for the minimizer than the first one. So it evaluates the other positions in the tree. The maximizer, after it searches the first 2 positions, it finds that it can achieve a score that is 9, which is greater than 6. Now, it knows that the minimizer can achieve a score that is no greater than 6. And so as soon as the maximizer sees a score that's greater than 6, it can stop the search. And there's no need for it to evaluate this last child of the second subtree. Similarly, as soon as the maximizer evaluates the first leaf node of the right subtree, which has a value of 7, it knows that it can stop the search because the minimizer will never take this path in the search tree because it has another path that guarantees it a score no greater than 6. And so this reduces the number of static evaluations that you have to do. The value of alpha beta really increases as the depth of the search tree increases. So this is just a bigger search tree that I'm not going to walk through in detail, but in this larger search tree, you have 11 leaves that are pruned. And in general, when you have a really good move ordering for your search tree, you're able to essentially square root the total number of positions that you evaluate. So if you always know the best move, you're able to square root the total number of positions that you expand in the tree. Okay. And we provide the code for alpha beta pruning in the search logic in search.c. Okay. Now, if I take a look at the files that are inside this directory, I'm going to search for search. All right. You see that there's a search.c, there's a search common, there's search globals, and there's search scout. Okay. So search scout is implementing what is called a zero window search. And scout search is an enhancement on normal alpha beta search that's able to increase the amount of pruning that you get. And it has a number of other advantages too that we'll get to. The basic idea of principal variation search or scout search is we can sometimes determine whether or not it is possible for a particular subtree to change the result by running a zero window search. So the idea is we assume that the first move is the best, and then we're going to run a scout search, which is a zero window search on the remaining moves to verify that they are strictly worse than the first move. So right here, the minimizer says, I'm going to assume that the first move in my move ordering is the best move, and I'm going to run a zero window search to verify that these moves are strictly worse. Okay. And the zero window search is good because in a zero window search, alpha is set to be equal to beta, and that allows more pruning to occur. And so whenever the zero window search verifies that all of the other moves are strictly worse than the first move, you're able to dramatically reduce the amount of nodes that you expand. So in this case, we verified that these two moves are strictly worse, and so we don't actually have to do a full window search. In the middle subtree, if we do the same thing, the zero window search, in this case, actually fails. So it found that in this zero window search, it found that it is actually possible for one of these moves to change the score of the maximizer. And so because the scout search failed in this case to verify that this move was worse than the first move, a full window alpha beta search is required. But we actually do the scout search recursively. So now we do the same thing. We now do a scout search starting from this position where we assume that the minimizer's best move is this move. And we're going to do a scout search here to try and verify that these moves are strictly worse from the minimizer's perspective than this move is. And in that case, the scout search actually succeeds. And this last scout search exceeds for the maximizer. Okay. So the logic for scout search is in search scout.c. Actually, the vast majority of the runtime in your bot is going to be spent doing the scout search, not actually doing the regular alpha beta search. So if you're when you start to look at optimizing the search logic, you're going to want to understand and spend most of your optimization efforts in the scout search logic. An advantage of the scout search routine from a chess programming perspective is that because we're just trying to verify that a move is bad, we're essentially doing a search to get a Boolean value. We want to know if a move could possibly improve alpha. And we don't actually care what the exact score is of that position when we're doing the scout search. We just want to know if it is possibly good or if it can be verified as bad. And because we're just interested in this Boolean, we're able to implement a bunch of speculative pruning strategies, like late move reductions, futility pruning, and null move margin pruning. All of these heuristics can actually change the score that you compute. But it's OK to use these heuristics in the scout search because we don't actually care what the exact score is when we're doing our scout search. And you can read about these heuristics on the chess programming wiki. And at the end, if we have time, I'll explain what these heuristics actually do. OK, so that's the basic. Those are the basic search algorithms that we use in this code. I realize I went through it really fast. These slides will be available, though, if you want to take a look more closely at them to kind of understand exactly what scout search is doing and how it interacts with alpha beta. Let's now talk about some of the move ordering heuristics that we use and the optimizations that we use in the search. Right, and Charles is noting that the actual URL for the chess programming wiki is now chessprogramming.org. Okay. So one optimization that we do is we do iterative deepening. So if we look at Leiserchess.c, we look at the code that begins a search from a given position. Okay, I forgot that there was a helper function around this. All right, so the actual search is performed in entry point in Leiserchess.c, and we do iterative deepening, where we search at depth 1, and then we complete the search at depth 1, and then we do a search at depth 2, depth 3, depth 4, and so on. And we do iterative deepening basically for two reasons. One is that if we do iterative deepening, our move ordering will tend to be better because we learn stuff about the search tree when we do lower depth searches. And additionally, iterative deepening is helpful when you are using time control, because you kind of have this guarantee that you're always going to have a move that you can report that you can play. So if you don't complete a search at a certain depth within time control, you can always report the last move that you found in the shallower search. We also use a transposition table. So a transposition table is basically a hash table. It's implemented in tt.c and tt.h. The transposition table is going to use the hash of the board position to store the score that was computed for that given position when doing a certain depth search. And the transposition table is very useful for allowing you to skip searches when you already have a search at sufficient depth to use. And it's also useful because often within a single search, the same position will show up multiple times through different transpositions of moves. And you're able to save a lot of work by memoizing the search result for those reoccurring positions. The hashing strategy that we use to compute a hash for the board position is based on Zorbrisht hashing. The basic idea behind Zorbrisht hashing is that each square on the board and each state of a square has a random integer associated with it. And the hash of a board position is the XOR of the random integers that correspond to the states of the squares. And because XOR is its own inverse, we can compute the hash of a position incrementally. So if we have a board position and we make a move, the board has only changed slightly. One piece has moved from one square to another, and we can compute the new Zorbrisht hash by just incrementally removing the old square hash and adding in the new squares hash. And there's a lot of creativity that you might consider implementing inside the transposition table logic. We have a pretty reasonable transposition table that we provided to you. Things to think about are what is a good eviction protocol for positions on the board. The transposition table that we give you is actually a direct mapped strategy. You might consider doing something that is set associative. You can collect statistics to try and understand what the hit rate on the transposition table is when you modify when you make modifications to how it's handling caching. In addition to the transposition table, we also maintain a killer move table. So a killer move table is basically recording moves that that led to beta cutoffs. And the idea is that if a move is good, in one part of the search tree, then it is probably also good in other parts of the search tree. So whenever you get a beta cutoff by making a move, you're going to record that move in the killer move table. And then when you are at a different position and you find that one of your legal moves appears in the killer move table, you prioritize searching that position first, with the idea being that if this move caused a cutoff in another part of the search tree, then maybe it will also give you a beta cutoff in the position in the search tree that you're currently at. And we index the killer move table by ply because you tend to see the same moves at the same depth. Additionally, we have another way to handle move ordering. So in general, for move ordering, we're going to do the transposition table moves first, and then we're going to do the killer moves second. And then we have a bunch of other moves that we want to order. And to kind of compute a heuristic score to determine the order of all the remaining moves that are not in the transposition table and are not killer moves, we use the best move history table. And so the best move history table is basically a big table that's indexed by the color of the piece type, the square that the piece is moving to, and the orientation of the piece. And the best move history scores are updated whenever a move is searched from a given position. So if a move is searched from a position P, and that move happens to be the best move from position P, then we're going to increase the best move history score by an additive constant. And if the move was searched, but it was not the best move, then we're going to decay the score of that move geometrically. And so this kind of, as you're doing the search, this is going to give a heuristic score to all of the moves in the game. And we use these scores to determine the order in which we search moves from positions. And the logic for the best move history table is going to be in search globals. So in search globals.c, there is this update best move history table, which takes in the index of the best move. And as you see, if for the best move, we're going to increase the score of that move by an additive constant. And if the move was searched, but it was not the best move, then we're going to decay the score geometrically by this constant 0.9. And so, as I mentioned, the typical move ordering is going to be the transposition table move, if it exists, is always going to be searched first. And then if a move is in the killer move table, then we're going to search those moves second. And then finally, we're going to use the best move history scores to order all the other moves. The way that we actually implement the move ordering.
How are the constants for the move table chosen?
They were chosen manually. They may not be optimal, but they're reasonable. It's not super sensitive to the exact values that you use usually. But you can vary the rate at which moves decay. It's important to make sure that you choose the decay rate and the additive constant such that the scores of the moves are bounded from above so that you don't get integer overflow. So that's the main thing to consider if you decide to modify any of those parameters, is you want to make sure that the decay rate is high enough relative to the additive constant such that the score is bounded and doesn't overflow. So what do we do with all these scores? Well, essentially, there's this function in searchcommon.c called getSortableMoveList, and it takes in a search node. It runs generate all, and then it's going to scan through all of the moves. And a move is like fits into a 32-bit integer. And so a sortable move is going to be a 64-bit integer that is going to use the upper bits of that 64-bit integer to store the search score. So here we see that if a move is the hash table move, we set kind of the maximum score. And if it's a killer move, one of the two killer moves, then we set a slightly smaller score. And then if it's neither a transposition table move or a killer move, then we're going to set a score based on the best move history table here. And then once you get the sortable move list, you can run any sorting algorithm you want, like quick sort or insertion sort, to sort the moves based on their score so that you can search them in the right order. Okay. So are there any questions thus far? Okay. I'll just take a moment to talk about some speculative search tree pruning strategies. So there are a bunch. These are implemented in Search Common mostly. So we have things like null move pruning and late move reductions. So null move pruning basically first tries to reduce the search space by not moving and then doing a shallower search to see if the subtree can still cause a beta cutoff. You can see exactly how we do this in the Search Common code. The basic idea is that if we make no move and we end up getting a cutoff, then probably this position is so good that the opponent wouldn't let us get to this position to begin with. And so we speculatively prune that position. And we only do this in Scout Search, again, because this obviously will change the exact score that we compute. We also have futility pruning. So futility pruning basically decides to prematurely stop a search when the current evaluation score is much greater than beta. Or much, right, yeah. So, and the idea is that if the score is much greater than beta, then it's very unlikely that additional moves will be able to improve the position sufficiently so that it will exceed alpha. And so in the search, let's see if I can find the, sorry, it took me a minute to find exactly where this table is. But for futility pruning, there's this table called fmerge, which basically gives you a score margin based on ply. And the idea is that if you only have two moves, if you only have one move to go, the futility margin is set to half a pawn value. And the idea is that if you're behind by half a pawn value and you only have one move to go, it's unlikely that one more move is going to increase your score by half a pawn value. And there is an entry for each depth that you have left to search. These values may be things that you want to tune a little bit, but these are what we provide to you at the moment. But the idea is that if you're behind by the fmerge, then you probably should just stop the search because you're so far behind that you're unlikely to recover given the remaining depth that you have to search. And then there are late move reductions. So late move reductions basically say that you're going to search the first few moves in your move list to full depth. So I'm going to search the transposition table move, the killer moves, and maybe the first most highly rated moves according to the best move history table to full depth. But then for the moves that appear later in the move ordering, the moves that I do not think are very good based on the move ordering, I'm going to reduce the depth that I search those moves. So I'm going to reduce the search depth for kind of the latter half of the move list. And Again, this is a heuristic that definitely can change the actual score that you compute. So we only use late move reductions when we're doing the 0 window searches in Scout Search. But it can have a pretty sizable impact on the gameplay and performance of your bot. And so we provide this heuristic to you in the reference implementation. Okay, so those are kind of the speculative pruning strategies that we use in the bot. You can read more about these on the chess programming wiki at chessprogramming.org. And in the last 10 minutes, I'll just mention a few other tricks that students have found successful, have applied successfully in the past. A really great thing to do at some point in the project is to develop an opening book to store positions at the beginning of the game that you pre-compute. And a good approach for doing this is to actually have separate opening books for each player. So if you're playing as Tangerine, you have a Tangerine opening book, and if you play as Lavender, you have a Lavender opening book. It is in fact known to be a lot cheaper to use these two separate opening books than to simply have a single opening book. In addition to an opening book, it's a good idea to think about developing an end game database. So you might consider having a database of all the positions that only involve 2 kings. So if all the pawns have been eliminated and you're left with 2 kings, you can compute an end game database that can guarantee that your bot plays perfectly from the end game position. And you might also go further than that and maybe handle the case where you have 2 kings and 1 pawn on the board, and try and guarantee perfect play in that case as well. And we provide some basic code to help you develop an endgame database if you choose to do so. Okay, so this is a really fun project. This is my favorite project of the class at the very least. It involves a lot of complexity and there's a lot of things to learn. Fortunately, there are also great resources, the course staff, of course, but also there are online resources, especially at chessprogramming.org, for you to kind of understand some of the concepts that are being used in the reference code that we provide you. Although the code is very complicated and this project has a lot of moving parts, the general principles that you've learned in this class for doing performance engineering still apply in this code base. You want to test often. So you want to, verify that when you make a change that only impacts performance, that it doesn't actually change the search logic. A great way to do that, by the way, is, actually to set up a little file, input.txt, that does a fixed depth search, like go depth 6. Then you can run your bot to a fixed depth. And it will tell you the sequence of moves that it makes. So you certainly want to make changes that don't impact the actual move that is selected if you are making a change that is only supposed to impact performance. I actually recommend to students that they are even stricter than that. I recommend that you try to ensure that the total number of nodes expanded in a fixed depth search remains exactly the same whenever you make a change that is supposed to only impact performance. So if you make a change to move gen or to the evaluation function that is not supposed to impact the actual search behavior, but is only a faster implementation of the reference code, then you should try to make sure that the node count here is exactly the same as the reference implementation when you do a fixed depth search. And you should try and make as many of your performance optimizations maintain this invariant as you can. It's very, most of the time when you make a change that changes the node count, most of the time it's a bug. So whenever you make a change, you really want to run these fixed depth searches and verify that the node counts remain the same. Additionally, you should make liberal use of the auto testing resources like the Java auto tester and the cloud auto tester to verify that your game playing program, after you make some optimizations, actually plays better than the previous versions of your bot. And also you should try and, whenever possible, develop unit tests to try and verify correctness and also serve as a debugging tool. So if you make a change and you don't understand why the node counts are changing, then you may want to kind of implement some unit tests or some function comparison tests in order to try and narrow down the reason for the change in search behavior. And in terms of general optimization tricks, we recommend that you start with the optimizations that do not affect the search logic first. So if you profile the code, almost all the time is spent inside eval.c in the reference code that we give you. So you should try and direct your efforts based on the profiling results whenever you can. And there's a lot of optimizations that you can make just to the serial performance. Eventually, you'll be making this bot parallel, but there's at least probably a factor of 10 in terms of performance that you can achieve just through serial optimizations before you even consider parallelizing this code base. So you should try and exploit all those serial optimizations before you start working on changes that involve parallelism or changes that involve changes to the search logic. And with that, I think I'll take any questions if anyone has any.
For this closed book, is there a limit to the size? Like, what's to stop you from just like computing optimal play for up to like the entire game?
Well, I don't think you'll have the time or computational resources to actually do that. From practical, but you could very well create a very big opening book, a very big endgame database. There will be a limit on the size.
I think we did have a limit on size because otherwise, when we do the cloud stuff, we have to move too many files that are too big.
Yeah.
And I'm not sure I think we better add that to our list of things to make sure we get out up front, earlier than later. You shouldn't work on opening book or in-game database first. That's the kind of thing that, and in fact, many teams do perfectly well with neither an opening book nor an in-game database. So it all depends. In this project, the key thing is that when you sit down and you try to figure out what it is you're going to do, you have to say, and how long will it take me to get, how much benefit am I going to get from this? And how long is it going to take me to get it done, take my team to get it done?
Yeah,
so,
the main thing, so I'm just pulling up actually some profiling data for the bot. The endgame database and the opening book are really things that you probably want to explore kind of in the latter half of the project. At the beginning of the project, you really want to focus on serial optimizations. Here's some profile results actually for the bot. You can see that the reference code that we give you has about 80% of the time spent just in one of the evaluation function heuristics in laser coverage. So if you can make laser coverage, 10 or 20 times faster, you're going to dramatically improve the performance of your overall bot. And so you're going to want to kind of, and as soon as you get laser coverage optimized, you're going to find that your bottleneck shifts to a different part of the code. And you're going to have a bunch of these hot spots that you're going to want to optimize. And those optimizations are really the low-hanging fruit when it comes to improving your game playing bot's performance. Once you kind of get all those hot spots and you have a reasonably optimized bot, that's the time you want to start thinking about things like the opening book and the endgame database.
So I think we can let other people go. So thanks, Tim. This was absolutely tremendous tour of what we have for this project. I think a lot of students start out historically, they start out quite intimidated by this project. There's about, I think, 4,500 lines of code, source lines of code that are involved. And it's like, wow, how am I possibly going to manage this? And, but really we've sort of structured this in a way that, historically every team ends up being able to do substantial improvement to, compared to the initial unoptimized bot. So you'll gain a lot of confidence after you get going. One of the things we're asking you to do is to do a design project. Do some design. That doesn't mean you don't do coding. It's that you don't have to submit a beta, but you do have to submit, okay, what have you found out and how are you going to plan to deploy your resources? Okay. And then you can do the beta. So it really is, there's a lot of moving parts. How are you going to do this? This type of skill, whether you're going to do network programming or file systems or, working on processor performance for some, application or whatever, or even if you never use this and decide you're going to go on and do something else, this experience will really give you a lot of understanding of how do you approach, big projects. Certainly a lot of what you want to do is write a lot of little tiny, toy programs that can inform you about what's going on, write tools, okay, produce a test infrastructure and so forth. So, how you lay your foundation. And that's kind of the focus of the design project. We'll talk about this in recitation tomorrow. So let's give Tim a hand, and then he and I will hang around for a little bit, and we can take any questions for people who have more questions about this project. Okay, so do some clapping. I think you can. Why don't you terminate the screen share so we can talk with people and take a look at the gallery. So do people have some comments? Okay.
This lecture has definitely made it very